Good morning. Today let us look at a buck converter which is a non-isolated DC to DC converter. Buck converters can be used to reduce the input DC voltage to a and provide an output voltage, output DC voltage which is smaller than the input voltage. Okay, so to reduce the input voltage to a smaller value and do that in an efficient manner compared to linear regulators or linear voltage converters. The efficiency of linear voltage converters can have efficiencies like 50%, 60% in that range or even smaller. But these switching converters will have efficiency of approaching 90 to 95% throughout its entire operating current ranges. So that efficiency is what differentiate the switching converters from the linear converters. So this is a switching converter which is of a high efficiency, close to 90-95% at full load. Okay, so in the actual lab experiment you will have to have you will have to use a DC power supply to supply this VCC and a particular circuit based on the SG3525 IC in order to generate this PWM signal. Okay, but in here, because it's a simulator, we have the flexibility of using a voltage source which can model or which can be configured as a PWM source. So I have kept these voltage sources here, one for the VCC and the other for the PWM generation. The VCC one I have configured as a DC 12 volt supply. Okay, and the PWM one I have configured as a pulse signal with pulse width of 10 microsecond and a total period of 20 microseconds. So it's a 50% duty cycle signal with a 50 kilohertz frequency, right? So that is the PWM configuration. And going back to the circuit, what we have in a buck converter is a power MOSFET, in this case IR540N. It can handle currents in the range of 20 amperes or so, 20 or 30 amperes, and its gate voltage, threshold gate voltage, it's an enhancement type MOSFET, and it has a gate threshold voltage and it's in the order of 5 volts or 6 volts. And this is intended for high frequency use as well, high frequency switching uses. It is intended to be used as a buck or boost converter active element. And then we have an inductor which is connected in series with with the transistor. So the drain terminal is connected to the VCC. The drain terminal of the MOSFET is connected to the VCC, and the source terminal is connected to the inductor. And then we have a electrolytic capacitor, in this case 100 microfarad, and the inductor is of 1 millihenry. And then I am using a second active element which is the diode, and in this case the diode model that I am using is that of BYG22D. This is the high frequency diode, and I have the data sheet also available. It has a very short or ultra fast reverse recovery time. That's why it's considered as an ultra fast diode, and you can use any of the ultra fast diodes. The model that I have available was that of this BYG22D, hence I used it. So you can use any of the other ultra fast diodes as well. So anything that can switch at this high enough frequency of 50 kilohertz. Right. And for the KiCad diode model, you need to, any of the KiCad diode models, you need to take this alternate node sequence and you have to write it as 2,1, because the native KiCad format is tailored towards the PCB layout editing and all those workflow. And there the node numbering sequence is inverse that of the node numbering used for simulation. Okay, so because the tool is catered towards the PCB layout, we have to reverse the pin sequence used in case of this diode. So for all, whenever you are using diode in KiCad for simulation, you ensure that you tick this alternate node sequence and specify 2 space 1. Right. So that is the specific about simulation. And then I have kept a load resistance or a resistor to simulate the load, which is of 1 kilo ohms. All right. And then the PWM signal is generated relative to this ground itself. So there the other terminal of the voltage source is grounded, and one of the terminal, the first terminal is used as a PWM supply. So here let us look at the source model itself once again. So the pulse value is 15 volts, and this takes care of the this ensures that the pulsed value is 15 volts. That's a peak value is 15 volts. This will ensure that in the steady state you will have sufficient pulse voltage to overcome the VTH, the threshold voltage of the MOSFET, right? Because this voltage needs to be equal to or greater than this VGS plus the output voltage VO. Okay, so VGS plus now VO in the steady state needs to be equal to PWM A peak voltage, otherwise the transistor will not turn on. Okay. So I have kept the voltage so that the transistor can turn on in the steady state also. Alright, now let us move to the simulation itself. So here there are no other parameters other than what is displayed and what we have already looked at. So so inductor has just one parameter, which is the Henry value or the inductance value, and capacitance has just the farad values, and resistance have the resistance value. Right. So let us move to the simulation itself. So simulator settings, and here I have already configured this to be having a time step of 10 microseconds, because if you remember in the source specification what we have given is for a 50 kilohertz PWM signal, and 50 kilohertz PWM signal means its on time is just 10 microseconds. So I just gave that value here in the time step, and the final time I have given it as 10 milliseconds. Run the simulation for just 10 milliseconds, because anything more than that it is going to give me a lot of data, and my simulation time is going to be extremely large. Right, and initial time of collecting the response is 0 seconds, and I am doing a transient analysis, similar to what you will do in the lab. So whenever you want to observe the output as a time series signal on a CRO, the equivalent in the simulation world is the transient analysis, and this will hence be the most common analysis technique that you will be using in all your circuit analysis, in all your academic projects. Okay, so this is the simulation configuration, and I click OK, and then I run the simulation. Okay, you can see that the time is incrementing, the simulation time is incrementing little by little, and I have a total of 49,744 data points in the x-axis. So there are total 49,744 time values for which an output is calculated, right? So let me probe some of the signals that I want to observe. So I first of all want to observe this output and the input voltage. And the input voltage, which is the VCC, it is shown in green, and so green you can see that it is steady at 12 volts. Okay, I have configured the voltage source for VCC as 12 volt source, and it is giving a 12 volt steady output. And the V output, which is the output of the buck converter, you can see that it is initially the capacitor was fully discharged. Sorry. So you can see that initially this capacitor was fully discharged, and slowly you first need to charge it up to the steady state voltage. Okay. So the capacitor needs to be charged, and after some time the steady state is reached, which is close to 6 volts, because we are giving it a 50% duty cycle signal. The output voltage is expected to be at 6 volts, and you can see over course of time in the steady state is reaching to 6 volts or slightly less than 6 volts due to the losses in the transistor, as well as the dynamic on time resistance or DS on of the MOSFET, and the forward voltage drop of the diode. Because of these two losses, you will see a slightly lower voltage than the theoretical 6 volts that you will expect here. So it's still settling. In order to see the final output, you will need to run the simulation for a lot longer in order to see the properly settled output. So in addition, now let us probe or add the signal. Let us measure the current through this L1, the inductor. So we have the main inductor here, the series inductor here, annotated as L1, which is of 1 millihenry. Let us see the current through that. So IL1 is the current through this inductor. So I am adding that one. So now I have the current through L1 in coming in blue. So let me zoom that in. So along with this, I'll also probe this PWM waveform. Then it will make better sense. Maybe I'll change the color of this one. So let me remove all these unwanted signals, and I just need to have the PWM signal and the current through the inductor. Let me add this current signal IL1. Now we have both the signals and both of them are visible. Let me zoom in. There you can see during the positive half cycle, the current through the inductor slowly increases, and then during the negative half cycle the current reduces. Okay. Similarly, you can, so this is as per your expectation based on your your textbook ideas. Okay. So similarly, with the different other components also, you can observe the current, the voltage across, or the terminal voltage, etc. better in this simulator. So this is one of the advantage of using a simulator. So you can very easily understand the current through individual components and the voltage across individual components, compared to using a breadboard and a CRO in the lab. So better visibility into the working of the circuit can be obtained by looking at the current through each of the various components. So you can observe the current through this diode, the current through this MOSFET, through the capacitor, through the resistor, etc. And you can get a better understanding of the working of this particular buck converter circuit, right? So that is the advantage of, so that's what I am stressing, the advantage of a simulator approach towards understanding these switching converters compared to a breadboard approach. So you have a better understandability, better visibility into the working of the circuit, and you can understand the working of the circuit much better by observing these various signals. And two things you need to observe are the effect of this PWM duty cycle on the output voltage. That is the first thing. And the second thing is the effect of the PWM frequency on the inductor current. Okay. So the effect of PWM duty cycle on the output voltage, I will leave that as a homework for you. So you can vary the PWM duty cycle, and so it's let us see how we can do that. So in the source specification, so right now the pulse width is for 10 microsecond and the period is for 20 microsecond. And if you increase this to say 15 microsecond and keep the period as 20 microsecond itself, then what you have is a 75% duty cycle signal. Okay. So that way, by changing the pulse width while keeping the period the same, you can change the duty cycle. You can vary the duty cycle of the PWM. So what you need is, you need to observe for different PWM values or PWM duty cycle values, what the output voltage is going to be, or how the output voltage is going to vary with the PWM duty cycle. This is what you need to actually do by yourself, and this is the part that you have to do in the lab also. Let us do a small experiment. Let us take one point which is at the 75% duty cycle case, and let us simulate that. Rest you will have to do yourself. We have modified the schematic, so by reconfiguring the voltage source, we need to save that, and then we need to go onto the simulator, and we need to run the simulation once again. Okay, so the simulator is stepping through and generating more and more data points within that 1 millisecond simulation time. And now you can see from the same region of the waveform that the duty cycle of the PWM, which is the yellow signal, is the PWM A signal, and its duty cycle, you can see that it is now 75%. Yeah, it is on for 75% of its total duration, its total period. So the duty cycle is 75%, and you can see the inductor current goes up during the positive half cycle, and then during the negative half cycle it drops down. all that is as per expectation. And what you need to look now is you need to get an outside view, and you need to see what the output voltage is going to be. Okay, so either you can probe or you can add signal as V output. Okay, so V output in this case is now close to 8 volts. Okay, this cyan line, it settles towards 8 volt or 9 volt. Okay, that is 75% of the 12 volt input. That is where it is going to settle down to. Okay, so we have previously seen that this V output is going to settle towards 6 volts in case of a 50% duty cycle waveform. Okay, and in this case it is going to settle towards a higher voltage. So the effect of increasing the duty cycle is to increase the output voltage. All right, so that is the first experiment. You will have to similarly do it for 2 or 3 of the other duty cycle points, and you have to observe what the settled output voltage V out is, the final value of V out or VO is going to be. All right. So I'll remove this this output signal, output voltage, and we'll move on to the second experiment, which is not very easy in the case of a real lab setup, but it can provide a lot of understanding as to the working of this buck converter, and also the limitations of simulator, which I have not highlighted yet. Okay, sorry. So here what we will do now is that we will reduce the frequency of this PWM source. So I'll, instead of 15 microseconds, I'll keep it as 15 milliseconds or 10 milliseconds in order to have a 50% duty cycle case, and here also 20 milliseconds. So I am changing the order of magnitude, or the instead of 50 kilohertz, what I am going to feed it is with a 50 hertz signal. Okay, so okay, and okay, save it and go back to the simulator and run the simulation. So you note the amplitude of this current signal. It is within the 0.15 ampere region. So in here we have just simulated for 10 millisecond, and that is the issue here. So the on time itself is more than 10 milliseconds, so we need to have at least a few cycles here. So 1 millisecond and 100 microseconds on time and a period of 200 microseconds. That's what we are going to simulate. Save it. So now you can see that the current swing is between, I'm going to zoom in a bit, between 240 milliamperes and minus 240 milliamperes. So that is what the current swing is. The peak is at 240 milliamperes. Right. So if I reduce this by one more order of magnitude, if I reduce the frequency to 1/10 of the current frequency, so 1 milliseconds and 2 milliseconds. So there you can see that the current swing goes all the way to tens of amperes. The current is in this purple or magenta color, and that swing goes to tens of amperes. So once it reaches to the steady state, which can be much later, the swing can be or the current through the inductor can be in the tens of amperes range. But what we have not specified properly here, or what I have not disclosed to you while drawing the circuit, is that the real life inductors will have another rating, which is the current rating that it can carry, because beyond a certain current, the inductor's magnetic core, the magnetics of the inductor can saturate. All right. So each of the real world inductor will have, in addition to this inductance value, a current capacity also, or a current rating also. Okay, beyond which the inductor core will saturate and it will no longer work like an inductor. Okay, so in majority of the real world inductors that you can attach to a PCB, which are of sufficiently small dimension, you cannot go to this tens of amperes range. Okay, so it cannot conduct these tens of amperes without actually saturating the core. So that is one thing that is not properly modeled. So once the inductor goes to saturation, the behavior of the circuit can be completely different. But because we are not modeling that part at all, we are not specifying the current carrying capacity or the saturation current of this inductor anywhere in this circuit diagram or in the simulation, we cannot model that, or we cannot show that behavior here. But in your practical lab setup, the inductor that you will be using will be having a realistic current rating. Okay, and if you are keeping the switching frequency, the PWM frequency, so low that the inductor current is large and it enters into the saturation region, then the circuit will no longer work as a buck converter, and the output that you will be getting will be completely unexpected values, and your transistor will start heating up and giving you problems. So those aspects are not modeled here, and that is something that you need to keep in your mind. And this period, or the frequency variation experiment, is intended to highlight this particular issue with a simulation circuit that you need to, or with a simulator that you need to keep in your mind. Not all the parameters related to an inductor, a capacitor and a resistor is captured in the simulation tool. All right. So in addition to that parameter, the inductor has a lot more parameters. Like it will have because the construction consists of multiple number of turns wound on a former. It will have a capacitance between these turns. So a parasitic capacitance will be. So lot of other additional parameters will also be there for an inductor. None of these are modeled here. Okay, that you need to keep in mind. But once you understand these limitations, the simulator is a very nice tool to understand the behavior of these buck converters. And in industry also, because most of these buck converters today that are designed today are using surface mount electronic devices. It is not possible to breadboard all these buck converters, and there in the industry we rely a lot on these simulator, on these EDA tools in order to design all these buck boost and all these DC to DC converter. But you need to be aware of the limitations here, right? So you can experiment with all these parameters and then you can understand the circuit a lot better. Especially the parameters that you want to experiment with will be the duty cycle, the frequency, the load resistance, the inductance. So all these parameters you try to vary, and of course the capacitance also you can vary. So each of these parameters you vary one at a time and see the effect. First you try to predict what the outcome is going to be, and then you actually vary it, and then you see what the output is going to be. Is it as per your expectation, or what difference is there? So that is a very nice way to understand these circuits and its working. Right. Thank you.